Hi, so we're going to start talking a bit about different probability distributions, and in particular, the first one we're going to talk about is the normal probability distribution. Um, and so, before I get into the details of that, one of the things that I need to mention about the normal probability distribution is that it's a continuous distribution, which is different from the distributions we've looked at so far. So, in the other examples we've done uh, in chapter 2 in this course, the types of probability distributions that we've been talking about have been discrete distributions. So, for example, if you have, you know, we've probably looked at something like x, p of x equals xi, and then we have different xi's. Like let's say you can win $30, you can win $50, you can lose $10, and then there's some sort of probability associated with each, right? This is a discrete distribution. We should make a note here. Right, and the reason we know it's discrete is because, there's only, well, in this case, there's only a finite number of possible xi outcomes. So 30 is a possible outcome, 50 is a possible outcome, but no numbers between 30 and 50 are possible outcomes. Negative 10 is an outcome, 30 is an outcome, but no numbers between negative 10 and 30 are possible outcomes. And so we can sort of separate, and that's what it means to be discrete. We can separate 50, 30, negative 10 as the possible outcomes, and then we can compute things about those probabilities. So remember when we first talked about the different types of random variables, we said that the two types of numerical variables were discrete and continuous. And so we are going to be shifting now from discrete variables to continuous variables. And they will be shifting back to discrete a little bit down the road. But as a brief example, of a continuous variable, let's just say pick a random number uh, number 1 between 0 and 1. And so, if I were to draw what this might look like, we'd have 0 and we'd have 1 here. And then our potential outcomes, let me pick a color, let's go with green here maybe. Our potential outcomes would be anything between 0 and 1, right? My wife's saying hi to me. Hi. Loves you. Anyway, right, so 0 is a possible outcome, 1's a possible outcome, and anything in between 0 and 1 is also a possible outcome. And so what distinguishes one of the things, I shouldn't say the thing, but one of the things that distinguish continuous from discrete probabilities is that we don't think of how we compute probabilities necessarily the same way. So one way we compute discrete outcomes or discrete probabilities is, all right, take all of the equally likely outcomes and then figure out which ones correspond to the event, say that xi is 30. And so fundamentally, it's difficult to think of continuous probabilities that way. For example, let's say I want to ask myself, let's call a number from here x, and let's say I ask myself, what is the probability that x is going to be between 1/3 and 2/3? Ready? And we put a little. I'll get the hang of writing on this thing one day, I promise. And so I'll draw 1/3 down here, I'll draw 2/3 down here. And we say, all right, well, if we try to think of this problem the way we've been doing discrete distributions, we'd say, all right, how many numbers between 0 and 1? Well, there's infinitely many of them. Okay, and then how many numbers are between 1/3 and 2/3? Well, there's also infinitely many of those, and annoyingly enough, it's the same type of uncountable infinity for both. And so if I pick a random number between 0 and 1, like from the old perspective, it would seem like it would be plausible that possibility is 1 or 100%, right? Infinity over infinity, the same values gives us 1. But that's clearly nonsense, right? Like, just looking at this thing, we should immediately know that this isn't the whole area. There's certainly stuff not between 1/3 and 2/3. And so perhaps a better way of thinking about it then would be to say, all right, that's 1/3 of the total interval here. So, that event, that probably ought to be 1/3. All right, and so one way of sort of reconciling this would be if instead of, let's say, pick a random number between 0 and 1, let's say, all right, let's shoot a dart randomly into a square, a 1 by 1 square, whose bottom left corner is 0, 0, and whose top right corner is 1, 1. And then let's now ask ourselves, what's the probability, right, that the x-coordinate of this dart, let's stick with the same question, is between 1/3 and 2/3. And so we note that this is the region of our square whose x-coordinates are between 1/3 and 2/3. And so that then turns out to constitute 1/3 of the entire square, right? And so one way of thinking about it is, all right, the square has area 1. The region associated with the event here, that has area 1/3. And so the probability then is that 1/3 region out of 1, which is just 1/3. All right. And we should note that this is not necessarily distinct from how we've been computing discrete probabilities so far. And so one of the things that I want us to reconcile in our heads is that going forward now, we're going to be kind of interchanging area and probability in our heads. And I'll probably be using the same language back and forth. Now we should probably put the equal sign in quotes, but right, well, how the way we want to think about probabilities going forward is as areas. All right. Uh, and to sort of reconcile with what we've been talking about with discrete probabilities, let's think about um, let's think about a concrete problem here. Let's say I flip two coins. Uh, I flip two coins and let x be the number of heads. Okay, so flip two coins and let x be the number of heads, then uh, what I want to know right now is what a probability distribution for this problem looks like. And so first I need to know, what happens when I flip two coins. So it's like what could happen is I could get two heads, I could get two tails, I could get a heads and a tails, and I could get a tails and a heads. Right? And so what it looks like to me is that there are four possible outcomes. One outcome with two heads, one outcome with zero heads, and two outcomes with one head, right? So this is half my probability space, and each of these is a quarter. And so if I wanted to sketch what that might look like, I might say, all right, here's 0, here's 1, here's 2, let me switch my color up here. I really like having an infinite palette of colors, even though I'm going to use a couple of them. And so I said, all right, if I sketch it like this, then this little rectangle represents no heads, and that's this event here. This rectangle here corresponds to one heads, and that's these two events down here. This third rectangle represents two heads, and that's this event here. And so if this is how my heights are measured, and let's say the base of all of our rectangles here have length 1, then this is a 1 by 1 quarter rectangle whose area is 1 quarter. Here's a 1 by 1 half rectangle whose area is 1 half. Another 1 by 1 quarter rectangle whose area is 1 quarter. 1 half plus a quarter is 1, so this thing has area 1, which is the total probability. And then each one of these rectangles corresponds to the appropriate probability. And so once again, I'm going to go ahead and reiterate area equals probability. All right. And this is going to be critical to how we think about the normal distribution. And so what is the normal distribution? Well, the normal distribution is a curve centered at 0 going to blah blah heading to both negative and positive infinity. That forms a It really should get closer to the x-axis in both directions. A bell curve type shape. You know what? I can do better than that. And so there we go, and it's centered at 0 here. And then the formula for the distribution is, or for the shape of this curve here, is y equals e to the minus x squared over 2 over the square root of 2 pi. All right. So this is a horrible formula, and the reason that it takes on this particular form is sort of archaic, and it's somewhat beyond the scope of this class. If you are interested in knowing more about it, then you can take Stat 341, which I'll be teaching in the spring probably. I taught it last spring. But for the purpose of this class, I just want to take a look at this this formula here for a second. Now the square root of 2 pi, that's a constant, so that never changes, right? The only thing that changes, that determines the height of the curve, is the x here, right? And so one thing we note is that when we take numbers to negative powers, that's the same thing as taking 1 over that power, right? So e to the minus x squared, e to the minus x squared, that's the same thing as 1 over e to the x squared, right? And so if we're just looking at that, there's some things we should notice. First of all, if I take something like, let me switch my colors up here. If I take like 3 or maybe 2 and negative 2, and I plug them in to x here, once I square them, right, if I take 2 squared, I get 4. If I take negative 2 squared, I get 4. So this value here and this value here will be the same. And that would be the same if I chose a number different than 2, right? If I chose 10 and negative 10, if I choose 1/2 and negative 1/2, if I throw them in there, it's going to be the same thing, right? And so the point of that is that the curve is symmetric, right? It's reflected. I can reflect across. Let me use gray here. I can reflect across this axis here, and it should be the same on both sides. What we also know is that x squared is always positive, right? And when I take e to a positive number, it's always positive except when x is 0. If I take e to a positive number, that always gets bigger. If I take 1 over a bigger number, that always gets smaller. The bigger x gets, the bigger e to the x squared gets, and the smaller the fraction comes. So as x gets larger, this thing gets smaller and smaller, and then that also means that going in the other way, it gets smaller and smaller too. And so the largest value that this expression, either of these expressions, can take on is when x is not positive. And that only happens when x is 0, or when x is negative. So since negative and positive numbers do the same thing. So when x is 0, then I just get 1 over e to the 0, which is itself 1. 1 over 1 is 1. And so this thing becomes just 1 over square root of 2 pi. So it's largest at 0. So that's the maximum of this curve here. Now, there are literally infinitely many probability distributions, and there's literally infinitely many potential families of probability distributions. So a reasonable question one may have at this point is, why focus on the normal curve here? Well, there's two answers to that question. One of them is something we'll discuss down the line in a future video. That's, in some sense, the more important answer. But we'll start with a relatively simpler answer, which is that, you know, lots of things in natures are normally distributed or distributed in ways that are similar to bell curves. So forget the zero and just look at the shape of the curve in general. Um, there's an average value right in the middle. The, the values that are close to the average are more likely, and the values that are away from the average are less likely. So if I wanted to say, for example, again, remember, areas and probabilities mean the same thing now, right? So if I want to ask myself, okay, what's the probability that something ends up between 0 and 2? That's that area there. If I want to know the probability that something lands between, say, 4 and maybe 6, that's that over there. And, it's pretty obvious just from looking at it that the probability you land between 0 and 2 and 4 and 6, it's higher here than it is there. And uh, even though both of these events, right, have a range of length 2, right? This is a range of length 2. This is a range of length 2. But these are way more likely because they're closer to the mean. These are far less likely because they're away from the mean. And so you can imagine that all sorts of things in the natural world are distributed this way, right? There's an average value. Stuff that's more like the average is more likely. Stuff that's less like the average is less likely, right? Although not impossible, right? There's still some area here. Okay. Um, and so, a question one might ask oneself at this point is, well, most things may be distributed, or many things may be distributed on a normal curve, but they're not distributed on a bell curve whose mean is 0. All right. So this bell curve we described here, this is called the standard. Let me switch my colors. This is the standard normal curve. And it's often denoted n mu equals 0, sigma equals 1. And what that means is that the mean of this, the mu, the average, or mean, is 0, and the standard deviation, or sigma, of this curve is 1. Now, there are other normal curves that have different means and different sigmas, but the important thing to remember is that they all fundamentally have the same shape as the standard normal curve. So I'm going to pull up this picture from the text here. Here's a picture of two normal curves. Without a y-axis, it's hard to tell if this is the standard or not. Given this range, I want to say it is. So this, let's say, is the standard normal curve, mean 0, standard deviation 1. And here's a normal curve with mean a little bit less than 20, standard deviation definitely a lot more than 1, right? It's way more spread out compared to the curve here. But the point is that this curve is essentially the same shape as this curve. All we've done is kind of shifted it over and stretched it out, right? That's the only difference. And so we're going to talk about the relationship now between the standard normal curve and just some other normal curve. So here's n mu equals 0, sigma equals 1. Whee! And over here, we're going to just draw a normal curve here. And we're going to denote the variables of this curve on the left with z's, and the variables here with x. And so what I want us to get out of this is that every single value on this curve has a corresponding value on this curve, and vice versa. That for every z there's an x, and for every x there's a z, and there's a way to go forwards and backwards between these two curves. All right, so we'll switch colors again, and we're going to talk about going from x's to z's. So here I have a value on the curve. Its center is at mu, and its standard deviation is sigma. So it's shifted over, right, zip, and then it's stretched out by sigma, or potentially pushed in if sigma is less than 1. So if I want to get that x value over to this z value, the first thing I want to do is shift it back over. So if I'm going from these back here, given some x value, the corresponding z value out to be that value, unshift the mu, and then unsquash by the standard deviation. And then if I want to go from z variables over to x variables, I would essentially just solve this thing for x, or what I want to do is go backwards, stretch out by sigma, shift over by mu. So my x variables are my z variables stretched out by sigma, shifted over by mu. All right, and that lets me go bouncing back and forth between these two curves. And the reason that's significant is because if I, for example, take this area here on this curve, and I take area here on this curve, these things give us the same area. And remember, area means probability. And so that means that I can, find out everything I want to find out on any normal curve by finding the corresponding areas here on the standard curve, and any area under the standard curve corresponds to some region under every possible normal curve. All right. So next thing to talk about then is that part of it, finding the area itself, right? So let's say I do have a standard normal curve. I guess I'll stick with red for now. Let's have 1 and 2 here. I want to know this area. All right, so we talked a lot about finding areas, right? But not how to. And given the sort of complexity of the curve which defines this area, we might imagine that this is somewhat of a daunting task. Those of you who know a little bit of calculus might recognize this area as the computation of this integral. If you don't know calculus, don't worry, because we're definitely not doing this. And that's a 2, right, and not a 3. And it hardly matters because each of the x squared is not integrable or doesn't have an antiderivative in terms of simple functions. So this is not an integral that's doable by hand. It's literally impossible to compute this integral. So how we would find these areas then is, hold on, oh, there we go. There are a number of things you can do. You can use a graphing calculator if you want. You can use a z-square table if you want, but I would kind of recommend against both of those. I'm sort of philosophically against graphing calculators. The TI calculators do the same things and have the same functionality as when I was in high school, and I graduated in 2001. And it's just not reasonable to me that a piece of technology could cost the same and do nothing after 2001, yeah, geez, 18 years, doesn't make any sense to me, especially not when you can buy a tablet for a third of the price that has like 1,000,000 times the functionality, and you can check your email on it too, on top of that. And z-score tables are even worse. It's 2019. I'm not looking at a piece of paper to figure out what areas are, right? Now, so I am all for using modern 2019 technology to do these computations. Now, to some people, not me, but some people, they may argue that, we don't want to rely on technology or something to do math. But first of all, this is math. This particular bit of math, finding these errors, is not possible without some kind of technology. Or, those tables are just someone else having done the technology for you and wrote it down on a piece of paper. So it's not really different. And second of all, is there a version of the universe you think that you're not going to be around, some kind of technology? If you're watching this on YouTube right now, that means you have access to technology. And I don't think any employer of yours ever is going to, deny you the tools you need to do your job when all it is a web browser. That doesn't seem like a lot. So I'm going to be using technology, and you should too. All right. So with that rant aside, here we have the mean and the standard deviation. So that's the mean, which is 0, and the standard deviation, which is 1. And so, again, we want to find the error between 1 and 2. And so if we read the description here carefully, it says enter the left endpoint A and the right endpoint B. So if I look back at my curve here, my left endpoint is 1, my right endpoint is 2. So I go, all right, 1, oops, wrong thing. Click 1, 2, right? That's about right. I mean, I drew this terribly on a tablet. This is what the curve actually looks like over here. Between 1 and 2, and we get, well, you can read it here or here. The probability is 0.3590512, and it actually goes on longer than that. For the purposes of answering questions in the homework, please always err on the side of being more precise rather than less precise. I mean, you can literally copy and paste these values here, so there's almost no reason not to just have hyper accurate precision when you can. Like it's just safer that way, so that infinity will recognize your solutions, and it's safer for real life too, right? Um, and we notice here that uh, ZA and ZB, those are the corresponding Z scores of A and B. Now, we are on the normal curve, so A and B are 1 and 2, and so the Z scores are the scores, right? Because we are on the standard curve. All right, so hold on here. Let's ask a different question. Let's stick to the normal curve, but let's ask. All right, maybe what's the probability that x is greater than 1.5? All right. So we're essentially looking for this area here, right? And what we notice that if there's x is greater than 1.5, um, that there's no real upper bound to this, right? And so if I go back to my curve here, I can set my left bound to be 1.5, but it's not clear, maybe right off the bat, what my right bound out to be. But we should note something that, you know, it seems like it's only between a little bit less than -3 and a little bit more than 3 that this thing has any significant value at all. That, you know, way out here, if I try to zoom in, here, like I can't even see the curve at this point, right? And you know, this is not very high on the side here. And so, you know, at a certain point, there's not a lot of area in the tails, right? Most of the body of this curve is just in this middle range here, that in the tails, there's really not much. And so, you know, say a million. And that will get me, well, pretty far out here, right? I mean, there's really no area there, right? So a million then is a pretty good placeholder for infinity. And so we get a accurate enough estimation of that area, which is about go away, 6.680721%. And notice that I could chop off a whole zero, and it doesn't really change this area because the difference between 100,000 and a million, well, it's 900,000, but there's no area out there practically. So like I can chop off a bunch of zeros and it makes really no difference at all, right? So what about a non-standard curve? So let's say I have a curve whose mean and standard deviation is not a million, or sorry, it's not 0 and 1. Let's say I have a curve whose mean and standard deviation let's say it's 112. All right. maybe these are the results of a standardized test, and clearly not graded out of 100, but you get points of a certain sort, and the distribution is such that the average outcome is 100, and it ranges from that. And let's say we want to know the probability that someone scores between 80 and 110. So I go down here to 80, I go up here to 110. I want to know that area. And so what I would do here is say, okay, I'm not on the standard curve anymore. I'm on a curve where the standard deviation is 12 and the mean is 100. And you may have noticed something down here. These red numbers, 100, 112, 124, 136, 188, 76, 64, these are counts by 12, right? So 100 plus 12 plus 12 plus 12, minus 12, minus 12, minus 12. Those measure the length of one standard deviation. And so it's telling you that what used to be 0, 1, 2, 3 is now 100, 112, 124, 136. And right now, because A is 1.5 and B is 10,000, it's still going way to the left, way to the right. And it's shading all of that. But that's not the area we want, right? We want between 80 and 110. And so we see that, we see this, and yep, we see that between 80 and 110 gives us this area here, this probability of 0.74988, whatever. And now we see that ZA and ZB are ZA and ZB are minus 0.1, minus 1 2/3 basically, and I want to say that's 5/6. And again, that's just taking the 80 and 110, subtracting 100 from each, dividing it by 12, and we get these values here. Actually, you can see the computation right there, right? It's the respective A and B values minus the mean over the standard deviation. That's exactly what this noise here is, right? So this will allow us, what this calculator does then is it takes your A and B values, it finds its corresponding z-scores, and then it computes that area on the standard normal curve and displays it. All right, so I think that'll be it for this video. It's run on for a little bit longer than I had intended. In another video, so what we've done in this video is we've said, all right, if we've given bounds of a probability, it will find you the area or the probability. And what we want to do next is say, all right, given an area or a probability, what are the bounds of it? And so we will be talking about that in the next video.